Hi everyone, and welcome to this webinar hosted by WindowMaster Clearline. Today's main topic will be how to design with sustainable ventilation technologies, mainly based on passive strategies with natural ventilation. My name is Kasper Raun, and I will be today's presenter. I work as a building performance engineer at WindowMaster Clearline. The duration of today's webinar will be maximum an hour. I will try to keep it a little shorter. I will answer all questions at the end of the webinar, but please submit written questions at any point during the webinar. This webinar will also be recorded and uploaded to our website. The purpose of today's webinar is to talk about a successful natural ventilation system. To achieve a successful natural ventilation system, we need to think about design and operation. At WindowMaster, we are experts in creating the control systems that operate natural ventilation, which is something we have been doing for the last 25 years. However, controls and operation systems cannot stand alone. A successful natural ventilation systems really begins with the overall building design, and therefore today we will take a look and focus on the design of the building, as well as the calculations that can go into finding the optimal free area of the operable windows and calculating the initial performance of the natural ventilation system. This really goes for all types of buildings. Natural ventilation has some limitations, but it can be used to some degrees in most projects. If you take a hospital, for example, it doesn't only consist of operation rooms and so on, but it also has lobbies, atriums, waiting areas, and so on, which are spaces ideal for natural ventilation. But today I want to put an extra focus on commercial office buildings. These are spaces where people often are stationary for a long period of time and spend almost a third of their hours throughout a day. Therefore, we think it's extra important to prioritize a great design with access to both fresh air and daylighting in these office spaces. For the agenda today, I will start with taking a quick look at what is natural ventilation, just so you have an idea of how we define it. When we look at natural ventilation, or maybe more correctly, a natural ventilation system, we really talk about an intelligent control systems with automated operable openings that are controlled based on both indoor and outdoor conditions. So these operable openings should regulate indoor temperature, CO2 levels, humidity, and they should operate based on also outdoor conditions. So of course the outdoor temperature, but also take the wind speed and wind direction into account. The natural ventilation system should optimally also be linked to the overall control system of the building and cooperate with other building systems. In most or in many of our projects, we see a mixed mode system. So a ventilation system where you utilize both natural ventilation and mechanical ventilation. And in this type of system, it's very important that the natural ventilation and the mechanical ventilations work together in the right way, so you can utilize the best of both worlds. It's also very important that natural ventilation and operable windows specifically operates correctly with, for example, solar shading, because here you can both have issues with physical interference between the operable windows and the solar shading, but the solar shading can actually also block the airflow going in through the windows. So when we look at natural ventilation, we really look at a complete solution where you have a building designed optimally for natural ventilation. You have the right components to operate a natural ventilation system, and you have it linked to the rest of the building. So quickly, why do we want natural ventilation in our buildings? For the users of the building, it's a great tool to give them more personal control. There are a lot of research showing the connection between personal control and the happiness of the users of the building, which of course also goes hand in hand with productivity and wellness. It provides fresher air, so more similar to what the air would be outside, of course. It doesn't go through a lot of ducts systems in the building, which can in some cases be dirty with dust and bacteria. And in connection to that, studies also show that we see a lot less occurrence of the sick building syndrome in naturally ventilated buildings, which can be things such as dry eyes or dry throat or headaches or dizziness. For the building owners, natural ventilation can help achieve building certifications. For example, LEED, which I will show an example of later, and in other building certification systems like the Living Building Challenge, operable windows is a must. It can also, of course, help reduce the energy consumption of the building, as natural ventilation requires no fan energy. And lastly, a natural ventilation system will have a quick return of invest. And on that note, I just want to quickly mention that in the future, or in the near future, we are going to release a short financial case that are based on natural ventilations or mixed mode, natural and mixed mode systems. This case highlights how these types of ventilation can increase satisfaction for the user and thereby productivity, which translate into a return of invest on a natural ventilation system of under 1 year, only based on increased productivity of the employees. An example of this type of approach for a building project is the tower at the PNC Plaza, which I will show that reference later, not in relation to this business case, but if you want to see how it can be used in a specific building projects, you can go to Palladino's website, who was a sustainability consultant on this and many other projects, and they often use the approach of describing how wellness features can be used in a business case. So the next point of the agenda is how to design for natural ventilation in our buildings. A problem that we often see, unfortunately, is that natural ventilation and operable windows are thought of too late in a building design phase or in a building project. So we see that the buildings are already designed when natural ventilation is brought to the table. And this is really unfortunate because the building has such a huge impact on the overall success of a natural ventilation system. So what we want to emphasize today is also really to think about natural ventilation in the early design phase, like you would also, for example, with daylighting. The overall building design impacts this type of systems in a huge way. So we want to emphasize that natural ventilation is something to think of in the early design phase. What should we then think of course, when thinking about natural ventilation in the early design phase? And the first thing that comes to mind is the building layout simply. Natural ventilation is based on 3 different strategies. So you have single-sided ventilation, cross, and stack ventilation. Optimally, you should aim for one of the last two, as these are the most efficient ones. Cross ventilation will of course be mainly based on the wind pressure, whereas the stack ventilation will also take the thermal buoyancy, the difference in temperature between inside and outside, into account. When thinking about the building layouts and what type of natural ventilation or what strategy to use, you need to consider very much the depth of the ventilated zones. So we usually say that for a single-sided ventilated space, you should maximum have a depth of the room of 2.5 times the room height. And for a cross-ventilated space, the distance between the two openings on the opposing or adjacent facades should be maximum 5 times the room height. If you have buildings that doesn't comply with this, or if you just want a more efficient natural ventilation system, it can be very beneficial to think about a way to utilize thermal buoyancy in your building. If we look at a case where cross ventilation, for example, is not sufficient for the building design, we have an illustration shown here. It's just a fictive office layout where you have an open office on both sides of the building, and we see a horizontal section. If we assume that we have a building depth or a distance between the facades of much more than 5 times the room height, what we risk is that we will transfer old air from the open office closest to the inlets to the open office closest to the outlets. And this is really something we want to avoid when thinking about the natural ventilation design and the building design in relation to this. A simple solution, one of many, but a good solution could be to implement a central atrium in the building. In this way, you ensure that both facades will be used as inlets, so the occupants in both open offices of the building will have a direct supply of fresh air, and all the old air from the occupied spaces will be exhausted in the middle of the building through the central atrium. A great example of this is the Baltimore Law School. In this case, you have a building design that was too wide for cross ventilation. So in this case, you would have old air transferred from one space to another if you try to utilize cross ventilation. So a central atrium was used in this building project. And as you can see on the figure to the right, all the zones throughout the building, all the stories, will pull air through the facades into the occupied spaces. So all the occupied spaces will have fresh air, and it will all be pulled towards the central atrium and exhausted through the roof. The overall indoor climate design or solution was designed by Transolar in this great project. And the potential of the natural ventilation showed that it could be used 40% of the time throughout the year. And this is mainly in a outdoor temperature range between 43 degrees and 64 degrees. So a very good potential for natural ventilation in this building based on the great design by Transolar. The next thing to think about in a natural ventilation design, which you can argue is maybe the most important thing, is of course the operable windows. You need to have the right amount of free area. It should be distributed evenly throughout the occupied spaces, and you need to avoid obstructions of the airflow. The free area of a operable window can times be tricky to define. It's not always simple geometry, but generally it's based on of course the geometrical opening area of a window multiplied by the discharge coefficient of a window. And for a standard top hung window, the discharge coefficient is typically around 0.65 and 0.7. This discharge coefficient will vary a little bit based on the window type. But when you're calculating this free area, it's really important to consider the placement of the window in the in the facade. As you can see on the right picture, you can see a illustration showing an operable window with a chain. And what you can see here is that the actual chain length, or the effective chain length of the opening, it is much smaller than the actual chain length of the actuator. And this is often the case due to the first part of the chain being used to push the window free from either the frame of the window or the wall as shown here. Another issue can be if the facade is actually covering the sides of the window, then the free area of the side of the window will of course be much smaller than if you just calculate the basic geometry of the window. So that's really something that you should think about when calculating the free area. And we actually have on our website, we have a tool, actuator finder, which I can show here. And this can be used to find an actuator, but it can actually also be used to calculate the geometric free area of a window opening. And here you can also include the mounting condition. So on a specific window profile, it will account for that profile and the mounting of the actuator. But the required free area that you need for a project will of course be depend on the specific performance that you desire for a project. But a good aim or good rules of thumb that we have found throughout the year is to aim for an effective free area corresponding to 1.5 to 2% of the ventilated floor area if you have cross or stack ventilation. And if you have single-sided ventilation, you should aim for around an effective free area corresponding to 3% of the ventilated floor area. Then when you calculate the required effective free area or geometrical free area, and you have found the necessary amount to achieve the performance you want, then if you suddenly implement something like a box screen, it can really reduce the airflow going in through the window. So this is something that needs to be taken into account early on. And the same thing goes with solar shading. If it's a very dense type of solar shading, it can really block the airflow going in through the window. So it's very important to consider when finding the right amount of free area in a project. Other than the necessary free area to achieve a good ventilation rate in your project, it's also very important, and it should be emphasized that the free area you find should be evenly distributed throughout the occupied spaces. Because in a natural ventilation system, our operable windows is really our inlets and our outlets. So if you have parts of the building where you don't have an operable window close by, it means that the occupants will not have a direct source of fresh air. So it should be evenly distributed throughout the window or throughout the building. And an issue that we see with this is really that in today's buildings, the window is often used as an aesthetic feature that is a part of the overall expression of the building. This can create problems or interfere with the natural ventilation design. But if natural ventilation is going to be used in a building, the ventilation effect or potential should really be prioritized. And the windows should first and foremost be located to provide the users with fresh air. There are many different types of operable windows that you can use in a natural ventilation design. As you might have noticed from the slides before, they all showed top-hung windows because this is really the most common type of operable windows used for a natural ventilation system, closely followed by bottom-hung window, because these types of windows are very great for precision control of the openings and can be very beneficial during colder conditions where you want to provide fresh air into an occupied space without causing draft. The top-hung window can also have the great benefit that it can be used during rain, which is an issue that you will have with some of the other types of windows. The side-hung window is a good option for a single-sided ventilation solution as it presents a taller opening area. However, it can be more difficult to control the draft rate during colder conditions, and the side-hung window will also demand more space if it's inward opening. So if you have anything close by, it will, of course, needs to be moved. Other types of windows like the parallel opening and the louvers are often chosen as a part of a architectural design. These types of windows can typically achieve a greater free area per window. However, similar to the side-hung window, it can be more challenging to control the draft rate with these windows, and they are also generally a bit more expensive compared to the top-hung and bottom-hung. The parallel opening window will typically require more than or multiple actuators per window, while the louver window will require a special louver actuator for this type of opening. The last thing I want to mention in terms of the building design is a bit more technical, but very important. It's what's called the neutral plane of the building. And the neutral plane is really what defines which openings vertically in the building will be inlets and which one will be outlets. So in a thermal stack effect, the neutral plane defines this. And you can say, when is this important to consider? It's always important to consider in a natural ventilation system, but it's especially important when you look at a building design like this shown here, where you have a large central atrium in the middle of the building, and then you have office spaces over multiple stories at the side of the central atrium. The issue with the natural plane in this type of building design is that you can get what we call backflow. And this is if you have the old air going from one office area or one occupied space to another. So some of the facades windows would in that case be used as exhaust. This is what we want to avoid in a building design. What we need to achieve this is that or to avoid that we have backflow, of course, is that we want the neutral plane to be above the occupied zones. To do this, we want the total free area of the skylights in the top of the atrium to be larger than the total free area in the facades. And this should optimally be 1.5 or close to 1.5 times larger. And this will ensure that we have a neutral plane that is above all the occupied zones. So all the facades openings will be used as inlets and provide fresh air to the occupants in the multiple spaces. To finish off, I want to discuss the general importance of locating the occupants closer to the outdoor parameter. As you can see from these examples, office examples, there's a big difference in the layout. And it's not only important in relation to natural ventilation. We have a lot of research that shows the importance of being near the outer perimeter and being connected with the outdoor environment. And it can be in relation to the window view, the positive effects from that, natural ventilation, of course, having something like indoor plants, and of course daylighting are all very important factors that can improve the experience of users of a building. This graph shows a lot of information, of course, as a lot more studies available than this shown here. And this is something that if you want to know more, you're very welcome to contact us afterwards. So to finish off the part of the building with the building design, I want to show a couple of reference cases with very different type of building designs. First, you have the tower at the PNC Plaza in Pittsburgh, in Pennsylvania. This is an amazing building. When it was built, it was the greenest high-rise building in the world. I'm not 100% sure if it still is, so I want to be a little bit careful, but it's definitely a very energy efficient and sustainable building. It achieved the LEED Platinum, which also indicates how efficient this building is. And natural ventilation can, in this regard, be a tool to achieve LEED points, for example. This table here shows some of the areas where natural ventilation can help achieve LEED points. And overall, it has the potential of achieving up to 22 LEED points. I won't go into too much detail about this. This can be a webinar in itself, but it's just worth to mention. The natural ventilation system in this building is based on a double skin facade, where you have the external windows, as you can see on the right picture, is these parallel pop-out windows, as also mentioned before in relation to the window types. On the inner part of the double skin facade, you have operable vents that allow the fresh air from the double skin facade to be supplied to the occupied spaces. Another great feature of this this double skin facade is that it can create and be used as an artificial outdoor space, where the employees of PNC can go enjoy a cup of coffee and so on. And it's actually this building here that I was talking about before in relation to the business case with wellness features, where Palladino was setting up the business case for the PNC Tower in relation to the multiple wellness features of the building. The pop-out windows and the internal vents are controlled by more than 6,300 actuators. In this building, it would also be too wide to have a cross ventilation principle. So to utilize the stack effect to pull the air through through the facades and make sure that all occupants are provided with fresh air, they utilize two central chimneys in this building. And in relation to the neutral plane, to make sure that all facades are inlets, you would need to have a larger free area in the roof, which is of course almost impossible in this case, as you have much more facade area compared to roof area. But what they do to help this problem is that they have a solar heated roof, which create an extra pull effect and make sure that all the facade openings will be used as inlets, and all the old air from the building will be pulled through the two central chimneys of the building and exhausted through the roof. The analysis of this building was made by Buro Harbel, so they created the whole design with the solar-driven chimneys, and it's a really impressive work. It resulted in a natural ventilation potential, where the natural ventilation could be used 45% of the time in this building. Yeah, which is a really great result for this type of building. Very impressive. Another impressive reference case is House Zero, placed at Howard University in Boston. It's a very different type of building than the PNC Tower. It's definitely not a simple building. There's a lot of different systems going into this, and it's the Center of Green Buildings and Cities at Howard are using this as an office building, but it's also a research facility. So there's a lot of technology going into this building here. But in terms of the ventilation design with natural ventilation, if you compare it to PNC Tower, it's maybe a bit more conventional, where you have high-level automated windows, which is used for natural ventilation all year. So you can say the strategy is more conventional, but they use natural ventilation throughout the whole year, which is pretty impressive in Boston. And the strategy is based on cross and stack ventilation. Then they also have low-level manual windows to provide extra comfort in the summer. And of course, extra user control, as I mentioned before, very important a tool to increase satisfaction and wellness of the users. As I just mentioned, the natural ventilation can be used or is used throughout the whole year in House Zero. And you can maybe ask, does it make sense to open the windows during the winter? But what we actually see in modern high-performance buildings is that they are so very well insulated and airtight that we often have a surplus of heat even at very low outdoor temperatures. Here you can see the different lines represent different internal heat gains in the building, different examples, and you can see with a internal heat gain of 20 watt per square meter, you can achieve or you will have a surplus of heat in the building even at the freezing point. So in relation to the energy consumption with heating, you can argue that it makes sense to open the windows during the winter. And I will just show a quick example of a strategy that we use for natural ventilation during the winter. We call it pulse ventilation, and it's basically to open the windows for a short period of time to flush a building, but then very quickly close them again. And this is a strategy that we have found works very well with human comfort in terms of how quickly a person will adapt to certain conditions. And if we only supply the cold air for a very short period of time, the occupants will not have the necessary time, or they will not feel the discomfort of the cold air, because it's just for such a short period of time. Just a quick note here, you can see the red scale, part of the scale is 900 ppm of CO2. So even though it might look a bit terrifying, it's not that bad. So right now you have around the yellow, purple or orange color, you have around 700-800 ppm. One of the design issues with House Zero was also the conference room here in the basement. As you can see, the ventilation can only be based on single-sided ventilation, which is a bit of a problem due to the large density in the meeting room. A very special solution for this building was to create a solar chimney. So similar to what we have in the PNC tower, but just on a whole another scale. And this, in combination with the facade windows, was able to create enough ventilation effect to regulate the air quality and the comfort in the large meeting room. So finally, I quickly want to show how our calculator can help indicate the performance of a natural ventilation system in a building. Before going into an example, I just want to quickly explain the results of the calculation that we have with this tool. As you can see on the first axis, you have the wind speed in miles per hour, and on the second axis, you have the air change in air changes per hour. The different lines indicates the temperature between indoor and outdoor. So the 20 degrees Fahrenheit is of course when it's colder outside, for example, and you have the large temperature difference. This can be used in a simple way to initially in the design estimate the air change needed to regulate the air quality. That's a pretty simple calculation. And the thermal comfort, it can indicate what is needed in relation to a steady state calculation, where for more details about the thermal comfort, you would of course need the dynamic simulations, which is also something that we can help with, but this tool here can not in itself do that. The background, I will jump through this very quickly, but if you want to know more about what equations the calculator is based on, you're very welcome to contact us, and we will explain more about the calculator. The case I want to, or the example I want to use for the calculation is a police station in the northern part of the UK. The reason why I use this case is just because it's a very, very good example of a medium-sized building with a optimal natural ventilation design. You can call it it's a textbook example, I would say, for natural ventilation. You have a central atrium with open office areas on both sides of the atrium, and you have the operable windows in the top of the atrium, which should work as the exhaust for the old air coming through from the open office spaces. On this picture, you can see more clearly the facade design of the building. If we zoom in a little bit, you can see they have both high-level operable windows and also medium-level operable windows. So it's a really optimal design for natural ventilation. If we look at the air change rate calculation for this building, I have quickly summed up some of the conditions. We have an area of around almost 3,000 square feet, and it's located in the suburbs. with 7 windows in the facade opening and 10 windows in the atrium, corresponding to a total free area of 35 square feet in the facade and 50 square feet in the atrium, which in relation to the neutral plane corresponds to, I think, the atrium opening being 1.4 times larger than the facade openings. And in relation to the rule of thumbs we had, the total free area corresponds to around 1.9% of the floor area. So I will quickly demonstrate a quick example of the calculator with this building. We have here on our website. It's very easy to find. It both have imperial and metric units. As I mentioned, it was placed in the suburbs. A building height or a height from the ground to the openings of around I think it's around 15 feet, and a room volume of 35,000 cubic feet. Then we can add the window groups here, where you choose the orientation. We say the facade windows is placed in the north side, has an opening area of 35 square feet, and is located on the facade. It's placed 6 feet from the floor, and the window height and the discharge coefficient we just keep as default. It fits very well. Then for the second one is the one at the atrium, where we have 50 feet of opening area. We set it on the southern orientation. It's not a skylight, so we just still define it as facade. But again, it's placed in a much higher location than the facade windows in relation to the floor. Yeah, again, we keep this default. Oh, what? Okay, sometimes it can be a bit tricky. But for this calculation, you can see here, as I mentioned before, you can see the air changes per hour. And if we relate it to a very simple steady state calculation in relation to the thermal comfort, we had an aim for around an air change of 5 times per hour with an indoor temperature of 75 degrees Fahrenheit and an outdoor temperature of 65 degrees Fahrenheit. So that's, of course, a temperature difference of 10 degrees Fahrenheit. And if we look at the calculator, it's between 8 and 12, so between 6.7 and 7.9. So in relation to the 5 times per hour, it achieves our goal. And this is just a very simple way where you can use a steady state calculation of the required ventilation rate needed to achieve a good thermal comfort, and use the calculator to see if the natural ventilation design achieves this ventilation rate. We have this reference case I showed was based in the UK, but we have many reference cases from the US, which you can see on our website or contact us if you want more information. So this was what I had for today. My 45 minutes is up, and we are ready for questions if you have any. Just to mention quickly, at WindowMaster, if you want help with or assistance with a natural ventilation design in a project, We can offer a lot of inspiration for natural ventilation solutions. We can help with basic air change rate calculations. We can help with dynamic analysis of a building. And we can also do CFD studies, both internally and externally. So yes, but I will see if we have any questions. So we have the first question is, if you have a combination with mechanical ventilation system with heat recovery from the exhaust air, what do you say about the heat loss through the open windows when the system is activated? Typically, when we have a mixed mode system with mechanical ventilation during the winter, we want to, of course, take full advantage of the heat recovery. And in almost all cases, you don't want to use the windows while the mechanical system is activated. So as I mentioned before, you can have cases where, based on high performance buildings, where you have a surplus of heat even at very cold conditions. And in this scenario, you can, if designed correctly, use natural ventilation, but then you would deactivate the mechanical system. So that's the whole point. So in most cases, in that type of mixed mode system, you would use these two systems independently. Then we have a question about the calculator in relation to if it can show just the results based on thermal buoyancy, so not with wind included. And right now, as you can see here, if you look at the first part of the graph, you will basically see the performance only based on thermal buoyancy with a very low wind speed. It's not something that we have right now with only thermal buoyancy shown on the graph, but it might something that we will add as an addition later to the calculator. And we are very, if you use this calculator and have feedback, we are very open for this feedback to improve the tool. And I can see the next question is also related to the calculator. It's based on the wind direction used in the calculator, if you're able to choose this. And right now, the calculator will automatically choose the worst wind direction, so the worst case scenario, and find the achievable air change rate at that point. But again, as mentioned, it's something that might be included in another edition of this calculator. Yeah, and then we have another question again in relation both to control, but also in relation to the result. That if you look at the result graph of the calculation, of course, when you have rising wind speeds, you will get very large air change rate. So of course the windows, the operable windows, should adjust based on this, based on input from the weather station. It will react accordingly to the wind speed and the wind direction to achieve the air change rate necessary based on the indoor conditions. So it calculates a optimal natural ventilation system, which the ones we do in WindowMaster. It will calculate the necessary air change rate based on the indoor conditions and adjust the windows according to that based on the outdoor conditions also. So then we have a question. It's about the chimney in house 0, the case I showed before. I can quickly go back to it. I think, yeah, here. Yes, so the question is if this kind of chimney is a more of a standard solution in natural ventilation designs, and this chimney used for house 0 was very much custom made based on a very specific project. But again, if you have a meeting area where you just have the option of single-sided ventilation, then it will be very difficult to provide a high enough ventilation rate to comply with the high density of occupants in this type of space. So in this solution, it was solved with a chimney, thermal chimney, which goes very well with the design of the house, you can say. And this is maybe something that would be another solution in a more traditional office design. Then we have a question about the window types. It's asking if the sliding windows, which is very common in the US, if that's a window type that is often used for natural ventilation. And the sliding window doesn't go very well in hand with the actuators because of the resistance that you often experience in those types of windows. There are solutions, or there are cases where someone has tried to deal with that kind of solution, but it's definitely not optimal, the optimal window design or window type for natural ventilation. Yes, so I don't think we have any, yeah, we have one more question. Yeah, that's a great question. Which products are used for air transfer from one room to another when the acoustics are an issue, for example, a classroom? And it's a great question, and actually the building I showed in the beginning, the Baltimore Law, I will quickly jump back through the slides. This one, it actually has rooms where they use special made transfer vents based on acoustic problems to transfer air from one room and out to the other, to the central central chimney, because the rooms right next to the central chimney is often is not often stationary areas, so it's more dynamic areas. So the issue with transferring air from one zone to another is not as bad. But I don't have slides right now showing the solution, but it's something I can send if you're interested in this. I can send it afterwards how they dealt with this. But the short answer is that you have transfer vent solution that can deal with acoustic issues, for example, like classrooms. It will have an effect on the flow rate because, of course, it's an added pressure loss in the system, but it is something that has been used in other designs before. So if there's not any more questions, I will say thank you very much for participating in this webinar. I hope you could use some of the information from today. And again, if you have other questions or want more information, you are very welcome to contact me or Window Master. Yeah. So thank you for today, and have a great day.